In the exercise at the end of the last video, we worked with this function and I asked you to show that it is Lebesgue integrable with Lebesgue integral equal to 1. Now you may have found it somewhat complicated or you may not have been able to solve it. So we are now going to take a closer look at this as well as the general technique of Lebesgue integration. Now this is a simple function because it takes only finitely many values 1 and 0. Now any simple function must have this form. So let me just write down the general form. In this case I am working with 0 to 1. Incidentally I have written AB here, I mean 0, 1. In general, indeed, I shall have A to B to R, and we shall not just work with R, we shall work with bounded function, so 0 to some m, so positive bounded function, m is some upper bound. And these numbers need not be only two of them, there may be any finitely many of them, C1 to Cn, and it will be in C1 if x lies in some subset of AB, which I shall denote by A1. Similarly, x in A2 and x in An. Now all these AIs should be disjoint, otherwise more than one rule will fire. And we also require the CIs to be distinct so that given any simple function, I can uniquely identify the CIs and the AIs. So the condition is AIs must form a partition of this, which means AIs are mutually exclusive and exhaustive. Their union must account for the entire domain, and the CIs are all distinct. This is the general form of a simple function. So here is a graph that I have given for a simple function which is far from typical. It is just to keep a picture in your mind. It takes only finitely many values. So these values are my CI. So this value is C1, this value is C2, this value is C3, this value is C4. They need not be ordered, but here I am drawing them like ordered. And this is AB. So where does my function take the value C1? It takes the value C1 over this set. So this interval is A1, this interval is A2, this interval is A3, and this interval is A4. But I must remind you that in general these things need not be intervals. For example, for the Dirichlet function, these were actually all the rationals and these were all the irrationals in the interval. The Lebesgue integral of this simple function is just total area under these things, which means for this one the height is C1, this rectangle, and the base is A1, so it should be C1 times the length of A1. Similarly for these it is C2, the height, times the length of A2, and so on. So it is summation I from 1 to n, Ci times length of Ai. Now the question is, since Ais need not be intervals, how do we define length of Ai? And it is this question that led Lebesgue to first create measure theory. Let us explore the question how to define lengths of subsets of some closed bounded interval AB. For certain subsets it is quite easy. For instance, if I take the entire interval itself, you immediately know that the length should be just B minus A. And in fact, this prescription works whenever you have any closed interval. If you take anything C to D, then its length should be D minus C. That is just obvious. Now let's make something a little bit less obvious. I want to define length of just the point C, which you already feel should be 0. Now you can write it as the closed interval C to C. So using this formula, this is just C minus C, which is 0. So singleton should have length 0. So immediately you can say that length of this semi-open interval is length of the closed interval minus the singleton C. But since the length of singleton is anyway 0, so nothing actually changes. So this should again be D minus C. And by the same reasoning, you can drop D also, no problem. You can keep C but not D, that is also not a problem. But you will always have D minus C. Now suppose I am interested in length of union of two intervals, two disjoint intervals. Isn't it very natural to say that it should be length of this plus length of this? And even if I take 3 or more intervals, as long as they are all disjoint, I should have the same result. In fact, I can do it for countably many intervals as well. Now let's really be ambitious. Suppose I want to find out length of this set. This is something that we needed to solve the exercise at the end of the last video, which was quite a difficult exercise. Suppose I want to find length of this. It does not seem readily obvious how I can find its length, but what I can do is that this is actually a countable set. So it is nothing but union of lots of singleton sets, I from 1 to infinity. These are all the rationals. And of course these are singletons, are either all distinct, so they are all disjoint. So its length should obviously be length of this, which means summation of length of all Ri's. Now these are all zeros, so it is basically 0 plus 0 dot 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 dot. Now you might be tempted to say, oh, that is undefined because there are infinitely many zeros, so it is 0 times infinity. But no, we know how to add infinite series. We just take the partial sums and take the limit. So all the partial sums, 0 plus 0 plus 0 up to some nth step, they are always 0. So the sequence of partial sums are all zeros, so the limit is 0. So this is just 0. So you have actually obtained from our common sense notion the fact that length of all the rationals should be 0. In this exercise, you have to work out the length of all set of all irrationals in the interval AB. We worked out the set of all rationals, but now you have to do it for the set of all irrationals.